so far we have studied topic that's basically what the basic definition of Fourier transform, and then we look at some functions in the time domain, and we find some of the corresponding Fourier transform. And again, you should have this understanding that Fourier transform is just a representation of the signal in terms of how it varies and what are the frequencies in the signal. So this is time representation, and this is like frequency representation. So two different representations. Okay. So this shows me in the time what are the values of my signal at each time, and the other one shows me how much of each frequency my signal has. With low frequency, high frequency, and those properties, like the frequency components of the signal, time and frequency. And we also saw that we have this duality between time and frequency. And so this is my signal in the time, this is my signal in the frequency domain, shown by capital T, and the parameter is x. Okay, so this is little g parameter T. This is capital G parameter is x. And you know, if I have G, I can easily find Gf by this formula. And then if I have Gf, I can easily get back my G by this formula. Okay? And you see there is very close relationship between these formulas. They are very similar. That's how we can get this duality of time and frequency. So going from this way to this way, we take a Fourier transform this way, and going from that way to that way is the inverse Fourier transform. Okay. So now let's look at some of the properties. Here, we discussed the time shifting and its frequency shift. Okay. So this is what we also had in the quiz. If I shift the signal in the time, so what it says, okay, if I have some GT, let's say this is my GT. Let's say this is my GT. It has some GM. Anyone remembers what the Fourier transform for pulse?
Same.
Oh, sorry, but something. Now, this formula, the top line, says if I shift my signal by some amount, let's say I shift it by 5. So therefore, instead of g of t, I have g of t minus 5. I shift it in the time by 5. So it says you don't have to, again, the integral find the Fourier transform. The only difference is that now your string function is going to multiply by e power of minus j 2 pi f times t naught pi. So you still have the same thing. The only thing is that now you multiply by this frequency, or this exponential term, e to the power negative minus j pi f pi. Okay, now the duality says the similar thing. It says, now if I shift this one in the frequency, so if instead of g of f, I have, let's say, g of f minus 2. So let's say I have a thing, and instead of starting from 0, I start from 2. So I shift my signal in the frequency. So what happens if I take the inverse Fourier? It's like my signal GC is multiplied by this exponential. See, the only difference is the negative side. E to the power of j 2 pi, the amount of shift, which is f naught, is 2 times 2. Okay. So therefore, instead of having pulse, I have this pulse multiplied by this exponential. So here, we are practicing two things. First, the shifting property, that if I shift the signal in one domain, doesn't matter if it's a time or frequency, in the other domain, I multiply either the time or frequency by the exponential term. corresponding exponential. If I shift in time domain, I multiply it by gf by this exponential. If I shift in the frequency domain, I multiply by dt by this exponential. So very similar case. Okay. And this is the formula for the duality. Is that if gt is mapped to gf, full transform of a gt is gf, capital Gf. Now if you look at that signal, capital G of s. Now if I treat instead of f, I put t. If I treat this as a new signal in the time, then if I take the Fourier transform, I'm gonna get little g. The only difference is that instead of t, I have negative. So hopefully during your homework, you could practice this because this was one of your homework problems to practice the duality. But this is the same thing that we talked about the other time. For example, if my little g is pulse, this is little g, capital G f is a sig. Okay. Now if I take this in the time domain, meaning that if I have a sync now in the time, what will be the Fourier transform? It's gonna be a pulse. See, if pulse is here, sync is there, and vice versa. If sync is here, pulse is there. So this is the duality. This is what we see here. Little g of t, if it's mapped to capital G of f. Now if instead of f I put t, see the apple rule. Instead of f, I just consider t. The signal in the time. So this is the apple. Then whatever I have is little g of minus. So take this one, just invert it. In this case, it's symmetric, so you don't see the inversion, but it's a function of f. Again, very simple rule. Just hopefully practice more and more, and yeah, this is a nice picture. So I have little g, I have capital G, and now if I take this in the time domain, this is the only thing that I did. Here I had f, right? My g was a function of f. Now apple rule, instead of f, I put t here. Everything else is the same. Because I replaced f by t, now I have a signal in the time. This is time, right? The same thing, but it's just in time. Take the Fourier transform, you're gonna get back that. You're gonna get the pulse. So this was my pulse. Little g of t. Apple rule. Instead of t, put minus f. Little g of minus f is a pulse of, instead of t, just put minus f over tau. And doesn't matter because it's symmetry, so you get this one. You look at it, this is only the same. Instead of f, you get just t. Everyone get that? Duality question.
You kind of already said it, but I just want to go over it because just to understand more. So if we have a function time domain, we change over the frequency domain. The frequency domain is continuous, so therefore we can just say it's basically a function of time and represent that same function as a function of time. And then from there we can say, well, the Fourier representation of that time domain is just the pulse function. Does that make sense? Am I getting that?
So you have your signal in the time, you take it to the Fourier domain, take it Fourier.
So now we have the frequency domain, and the frequency domain is continuous, right?
Yes.
So we can just say, well, let's just substitute in t since t is continuous. So now we have a separate function of t, and so.
Yeah. So now you have a function of t. Yes.
Exactly, and so then we can just
again
say.
Take a Fourier transform, and interestingly go back to that.
Yeah.
It's like a cross thing, you know. That gives that, and then if you consider that as a time domain, now this is a sync in the time domain. Take a Fourier transform, you get a pulse in the frequency. This is time domain, this is frequency domain. Okay. So whichever you have in the one domain, if you have a pulse in one domain, you are going to have a sync in the other domain. So pulse in one domain, sync in another. property. Again, very nice property. So it says if you have some g of t and the Fourier transform capital G of a. Now, if I scale my signal in the time, okay, so basically it says if I have some, let's say, G of t in the time, and then I have some G of a, so signal reduces it, let's say, and simply okay. Just now, if I have a scale, if I have g of a over 80, anybody remembers how g of 80 looks like? Cn. Sorry. So what does this one look like? Divided by a. Okay. It could be conversion pretty straight depending on what's the value of a, but this is c over a. Okay. So now it says if you do this multiplication of your signal, what happens in the free domain? Your g, instead of now in the time you multiply by a, in the frequency you have to divide it by a. Okay. So if this was like a stretch, let's say this was a stretch. Now in the frequency it's a conversion, meaning that this here is half here and here. And then a scale by 1 over actually like that. So what it said if you stretch your signal in time, you are compressing in that frequency domain and vice versa. If you compress here, you are gonna stretch it. See, one of them is multiplied by a, the other one is divided by a. Okay. So let's first prove it and then we're gonna see this. So basically what I want to find is the Fourier transform of g of a. So by the form, by the definition is just the signal e to the minus j2 pi ft. This is just the definition. So the common trick here is that because I have g of a t, I just consider this a t, the whole thing, as one other variable. So I have a change of variable. So instead of a t, just put x. So define this change of variable. So a t is x. So if a t is x, instead of t, I can put x over a. So instead of t, put x over a. What happens to dt and dx? What's the relation between dt and dx? If a t is equal to x, I can take a times dt equal to
dx.
Yes. So therefore, instead of dt, you have to put dx over a. Dx over a. So now, I mean, as you see, it's very similar. Like 1 over a over a. And then look at here. Integral of g of x e to power minus j 2 pi some f times x. So this is like if you compare it with the definition of the Fourier transform, integral of g t e to power minus j 2 pi f t t. See this f, this is f. Now here instead of f, I have f over a. So f over a, f over a. Again, upper root. That's how you get g of f over a. Because here you have f over a. And then you have 1 over a here as well. And that's it. Now, depending if a is positive or negative, okay, we have to measure one thing more. Here you have minus infinity and infinity, right? So the t, if your t is minus infinity, And if your A is positive, what do you get? It is minus infinity, your A is positive. What do you get? Twice minus infinity. Again minus infinity. And plus infinity. That's good. But if your A is negative, let's say your A is negative 1, and your T is minus infinity, what do you get for X? Plus infinity. Okay. So when you change the variable, you have to consider all the changes. Here the variable was T, you are converting to X. You have to change everything to X. So this is T from negative infinity to infinity. Here is X is, again, because if A is negative, now becomes plus infinity to negative infinity. And you know that if I want to convert it, like reverse this, I introduce a negative sign. That's how we get a negative sign here. If I change this from, instead of plus infinity to negative infinity, if I say negative infinity plus infinity, I introduce a negative sign. Okay, some manipulation of the formula. And anyway, so this is A positive, this is A negative. If you can put both of them together, you are going to get this one. You see the absolute value, that's why, because both positive and negative you have, and the sign is different. Okay. So please go over this proof again yourself, all the steps. This is a very classical method of proving this kind of correspondence. You want to find the Fourier transform of a new signal in compared to what is known. So you have to compare them and then just make them look the same. Okay. If it's X, it's good. If it's G of X, I know that. So I can convert it. So you have a change of variable. And when you do the change of variable, you have to take out all the changes. So again, very, very useful technique here. Definitely understand how it works. Okay, good. So basically we proved it. We proved that if I scale my signal with the time, what happens, my frequency domain signal is going to be inversely scaled. And then also it's one. So let's see one example again. Going back to this. If my G of T is that pulse, if my G of T is, let's say, this pulse of T over tau, let's do it. Let's calculate the numbers. Let's say if I have a pulse, like the numbers here, let's say this is from -2 to 2. So this is the pulse, which can be written as single T over
4.
4. This here is also the element duration. So this is mapped. If I take the Fourier transform, this is going to be mapped to a sinc function which is 4 times C of 5 4 5. So here, the first law here is 1 over tau, and my tau is 4 0. GTGF. if I scale my signal instead of g of t, let's say consider g of 2t. Okay? And this is g. G of 3t. So am I stretching or compressing?
Stretching.
Who says stretch?
Oh.
No, gt, just gt. If I have only g of 3t. Compressing, right? Because everything has to be divided by 3. So I'm just compressing here. So I my new signal what would be here? 2/3 and minus. See, from here, this signal to this signal, I compress it by factor of 2 because of this. 3 here. Effectively, you have to divide things by that. So this is my new signal, a shorter signal in the time one. So for the frequency domain, the formula says, okay, this is your g of 80. Now the Fourier transform is 1 over absolute value of A. What's A here? The scale is 2, right? So here it says, okay, 1 over absolute value of A, which is 1 over 3, times G of F over A. F over 2. Okay. So the property says G of 3t is mapped to 1/3 of G of F over 2. We can take the Fourier transform 1/3 of G of F over 2. Everything is divided by F. Okay, good. So now that's my G of F. I know how to scale things, right? Is it compression or here as you saw it was compression versus that. You compress the signal. Make the duration smaller. What happens here? What should I do? I'm scaling by 1/3. What's the effect here? Where does this one go? 3/4 multiplied by 3. So basically this is the direction. Instead of 1/4 to 1/4, you're going to have 3. So I basically divided these by 1 over 10. Or in other words, I multiplied that. Okay, I also have to change the magnitude here. I have to scale it by 1/10. So instead of 4, I have, what do I have?
4/3.
Here. So as you see, it's like in the frequency domain, I stretch that part for that same function. So it's stretched. So compression in one domain corresponds to a stretch in the other domain. And you see the formula was not really a scale, right? Just 1 over A, G of F over A. This is scale. Any question here? Everybody got it? So significance of this time scaling property as I thought. So g of at just represent the, let's say if a greater than 1 is a compression in the time, and then in the frequency, expansion in the frequency. So compression in the time domain is expansion or stretch in the frequency domain and vice versa. Expansion in the time is the compression in the frequency. So again, this is one of the basic things that definitely you should remember forever. That if in the time domain you compress your signal, in the other domain you are stretching. And somehow makes sense. When I compress a signal, see what happens. Instead of this signal, let's say if I have this signal, if I compress it, okay, if I have everything in a shorter amount of time, so I'm introducing basically more frequencies. Because if this one has longer, and then this one I'm just compressing the time, so I introduce more frequency. So therefore, correspondingly, what happens, whatever frequency that you have, now you have to have a larger frequency because you're increasing your amount of the frequency. So if you have, let's say, up to 2 kilohertz here, maybe now you have up to 8 kilohertz. Again, because you have compressed this. Okay, in the time you have compressed it, so you have introduced more frequencies. Okay, makes sense? I don't remember. I mean, I don't know if you remember those magnetic tapes. Do you remember? Okay. Audios, yeah. Cassette, yeah. So now there was a button like fast forward. If you push the fast forward, have you seen what happened? So basically, by fast forward is if there's something from let's say music lasts for 10 seconds, you wanted to hear it, or when you fast forward, you will hear it in 1 second, right? Like that. And that exactly is the higher frequency. You know, because you were compressing your audio in the time. So what would happen when you listen to that, basically you hear more higher frequency. That's why you will hear that funny sound. So basically that's the higher frequency. So again, compressing in the time. So because everything has to happen in a shorter amount of time, right? Everything has to happen. In the frequency, you're introducing more variations, and more variations means that you're increasing your frequency. So frequency and variation are basically hand in hand. If your signal varies in the time, again you have audio, and if you want to listen it only to 1 second, you're fast forwarding it, you have to increase the amount of variation, and that introduces higher frequency. And also vice versa. If for some reason you stretch your audio, if instead of 10 seconds you want to listen to that in 20 seconds or 1 minute, can you guess what is the sound? It's gonna be yes, like it's gonna introduce lower frequency. Low, so like lower frequency. Yeah. So lower tone, if you basically stretch in the time, means compression in the frequency. Compression in frequency. So you will have a more low frequencies. Okay. So again, you'll hear something like more like a whoa, or something like lower frequency versus which is more higher frequency. So like that. Okay. So intuitively, time compression means the signal varying more rapidly, so introduces higher frequency. And time expansion means that signal varies more slowly, hence the variation is smaller and you have more. Okay, I think this is a nicer picture. Again, back to the sync and pulse. So from here to here, did I compress it or stretch my time signal? From top figure to bottom figure. Did I
Stretch.
expand it or yeah, expand or stretch? Very good. By factor of 2, in the time domain I stretch. So in the frequency domain, the same factor of 2 is gonna be compressed. So that's why you see a narrower pulse here than there. Okay, instead of 1 over tau, I have 1 over 2 tau. It's much lower frequency. Into this is lower frequency. Okay. Okay, so again some more intuition. If G of t is wider in the time domain, in the spectrum domain is gonna be narrower. So time and frequency are like reciprocal each other, Your signal is wide, your spectrum is narrow. And vice versa. If your signal is really, really narrow, okay, your spectrum will be wide. Again, because here we have higher frequencies. If this is small, we have higher frequencies. So doubling the signal duration halves its band. Okay, if you double the time, you make it half of the frequency. And bandwidth of a signal is inversely proportional to the signal duration itself. And now that there was a mention of bandwidth, let me go back to this slide, which I skipped it the other time. Bandwidth is a very useful parameter for a signal. If you have a signal in time domain, and if you convert it to the frequency domain, and you look at the spectrum there, or frequency transform there, if you have something clean like that, this says, okay, my signal start, like the frequency starts from 20 hertz up to 100 hertz. So the bandwidth that I have is between 20 hertz up to 100 hertz. So the difference is 80 hertz. This is what we call the bandwidth of the signal. So the bandwidth is nothing but just the difference between the maximum frequency that I have, Fmax, and the minimum frequency that whatever is here is gonna be called the bandwidth of the signal. Okay. But a lot of time, like for example in this case, what's the bandwidth here? What is it?
Infinity.
Infinity, right? Because as you see, for example, my signal starts from the DC and then goes up to infinity. I have all the frequencies. The bandwidth theoretically is infinity. However, for this same function, you can say, for example, that most of the energy is in the main lobe. Call this lobe, okay? So in the first lobe, we have most of the frequency, and after that, it really becomes smaller and smaller. So somehow you can say, okay, so let me just consider this as an approximation of the maximum frequency. So therefore, if this is the maximum, like if I approximate maximum frequency like this, my bandwidth would be 1 over tau. So the bandwidth can be approximately 1 over tau hertz. Okay. So therefore, for a signal which has a duration of tau second, if I have a pulse that lasts tau second, the bandwidth is 1 over tau hertz. Okay, and always they are reciprocal of each other. So that's how we can also say it again that if I increase the time, I start decreasing the bandwidth, I'm decreasing the frequency. And all this duality that you see is present. Any questions? Okay, so bandwidth of the signal is inversely proportional to the signal duration. So now let's see some examples. Show that g of minus t is equal, is mapped to g of minus a. So it says if you reverse the signal in time, what happens is the frequency is going to be also be reversed. And this is just a special case for the scaling property. That's we don't need to include it because in general we know that g of at is mapped to 1 over after value of a G of f over a. So I know that this is the general case. So now if I have g of negative t, what's a here?
-1.
Negative 1. So if I, so a special case that a is negative 1, it's a special case, a equals negative 1, so it's gonna be mapped to 1 over absolute value of negative 1, g of f over negative 1, negative 1. So it gives me 1, and then g of f. See, very simple. Now that you have the general case, you can see the. So negation in the time corresponds to the negation in the frequency. Now it says use this formula to find the Fourier transform for this signal, each bar AT of minus t. Okay. So I already know this formula, g of t. If I have g of t, each bar of minus ATU of t, my g of f is, anybody remembers? This is again classical signal that everyone uses. That was g of f. 1 over a plus j 2 pi f. Again, if you remember Laplace, this is s, right? S plus f. The whole thing is s. If you're familiar with Laplace, a lot of things you can just correspond with the Laplace, and that maybe help you to correspond things better. But anyway, so g of f is that. Now instead of g of t, I'm given g of negative t after t. Instead of t equals negative t, instead of t is negative t. And then now the question is that what is the Fourier transform of this? The property says if you negate the time, you can simply negate the frequency. So you're gonna get g of minus f. What's g of minus f? Anybody here? What's g of minus? 1 over? Good, instead of f just. Okay, very simple. So you negate the time, you negate the frequency. Now let's look at how they look like. E to the power of negative ATUT. Looks like that. You have seen this a lot. At 0, what's the value at 0? 1, and it drops like that, and because of the UT, you have all straight. This is G of t. So G of minus t. I have to just mirror this, right? This is how the G of minus t. Okay? Good. So for that one, this is a Fourier transform. For this one, this is a Fourier transform. Now if I combine these two together, if I have something like that, let's say if I add these two, and I guess if I add those two, I will get yeah. Okay. So what do you think would be the Fourier transform of this? So this is GT plus G of minus. What does linearity tell you? If I add two signals in the time, what happens to the Fourier transform? Add it again, like add this plus J plus L. So this is kind of the Fourier transform for this. The signal. Okay, to multiply this two, what do we get? I mean, if I add these two, I have to make the common Cancel each other off, so I get 2a, and then multiplication of these two, giving a squared. What do you take with the next step?
Minus 2 pi f squared.
Minus 2 pi f squared, and then I have a j squared as well. J squared gives me j. So this is gonna be the Quaternion for the summation of that. So anything that I wanted, if I add these two, if you want to remove because u of minus 3, again, there's a problem with u of 2, right? And this is continuity. So I can consider that t equal to 0 is half. So this is the proof, and this is the whole thing I can write that e power minus a absolute value of t. Quaternion transform is just that summation, and we're gonna get that. So then the time is over. So we are gonna study more of properties of Quaternion transform, but I guess we are gonna, I mean, it's gonna be very easy from now on. Very easy now. Kind of small, so we have to